Recording. Okay, so this week's laboratory is lab A2B, which is bromination of E stilbene, shown here. Make sure in your report that you actually have E stilbene drawn, not Z stilbene. Just one thing to note. So E stilbene is going to be brominated rather than with a traditional brominating agent such as bromine. We're going to be using a bromine equivalent of pyridinium bromide per bromide. And in this case, the pyridinium bromide per bromide serves as a bromine source. And in this case, the bromination mechanism is exactly identical to that of your typical electrophilic addition of bromine across a double bond. We end up with attack of our double bond on the electrophilic bromine atom. We generate our bromonium ion intermediate, and then the bromonium ion intermediate is opened by an equivalent of bromide. The exact carbon that is attacked doesn't matter in this case because both products are identical. Addition of bromide to open up our bromonium ion yields the following meso product. Note that this compound is not optically active and this molecule is completely symmetrical, and you can prove that via rotation of your carbon-carbon bond. So this is the meso stilbene dibromide. You may have to look up this compound's physical properties using the IUPAC name rather than the informal name. So as the reaction takes place, our product will actually precipitate out of our organic solvent of acetic acid. We'll be able to isolate our precipitate and isolate our product via filtration, followed by triteration, or more specifically, rinsing with water. So we're rinsing with water, and this is a solvent that the product is insoluble in, and it's designed to dissolve our water-soluble impurities. This procedure is known as triteration, where you agitate an insoluble solid in a solvent in order to remove soluble impurities. Technically, if you wanted to do a more rigorous triteration, you'd take your solid and you'd physically agitate it with a stirring rod in the presence of your solvent, and then you'd filter off the supernatant liquid. But this method is fine, as the water rinses should remove the majority of any present impurities that won't evaporate off. The final step in order to dry our material and to eliminate the presence of water. Oh, sorry, someone's microphone is. Does someone have a question? Oh, sorry. Okay, so continuing on, after rinsing with water or triturating our solid with water to remove the soluble impurities, we're going to be adding acetone as a drying agent. One little issue with acetone is that our product is slightly soluble in acetone, so we have to rinse with cold acetone, and even then we lose a little bit of product during this drying step. Just something to note. There may be alternative methods to dry a sample, and you can refer to alternative techniques found in your lab manual. Now, once we've isolated our solid after air drying, we'll be able to calculate the percent yield by taking the isolated mass over the theoretical yield. You're going to need to calculate the theoretical yield from the experiment reactant mass from the video. You need to watch the video, and I'm going to expect students to record the exact mass of reactant weighed out in the video. This is important because you don't want to over or under report the yield because you're not using the actual values measured. Does that idea make sense?
Yes.
Okay, so the next thing we're going to do is we're going to take a melting point. So in our melting point, we load our capillary with our solid. It's going to be evacuated to minimize reaction with air and degradation due to reaction with air. We're going to record a T initial and T final. The T initial is when you first observe the liquid drops. The T final is when the entirety of your sample has melted. Typically, a melting point range of less than 1.0 tells us we have a pure sample. If impurities are present, we'll see a depressed melting point range and a broad melting point range. So for example, our pure melting point range, if it's 110 to 110.8, the impure sample would be like 108.5 to 110. So not only do we have a lower average melting point value, but the melting point range is broader than the pure sample. This is important to note because the melting point gives you a sense of the relative purity of your sample. Does that make sense to everyone?
Will we be using 4 significant figures?
Yes.
Okay.
You can report in calculations significant figures based on your input and output data. So if you're given values in 4 sig figs, you should perform your calculations using those values following significant figure rules. Does that make sense? Perfect. So we're also going to take IR and NMR spectra. These are useful for identifying and determining the chemical identity of your product. You're going to compare the IR and NMR spectra to the reactant E-stilbene and the product mesostilbene dibromide. Typically, IR and NMR give you an estimate for and are useful for determining the chemical identity of your product. They're not so much useful in terms of determining the percent purity. You typically have to get detailed integrations for your impurity peaks and have an idea of what your impurities are in order to use NMR to calculate the relative purity of your sample. So when you look at your experimental IR and NMR spectra, I'm expecting you to process these spectra into data tables. So for the IR spectra, you'll have your data table with your table title and description. It should have the wave number for each major peak and the signal intensity, where it's medium, strong, or weak, and BR for broad. So for example, this signal at 1700 should be 1700 centimeters inverse for the wave number, and it should be a strong or sharp peak. For proton NMR, I should see a table of chemical shift, integration, and multiplicity. So if you have a peak of around 5.0 that looks like this, with an integration of 2, you would note that it's a 2 hydrogen integration, and since it is a triplet, we'd note that it's a triplet. Yes, the experimental spectra should be included in the data section with the data tables below the spectra.
So are we analyzing both IR and HNMR for the reactant product?
For the reactant and product compared to your experimental IR and NMR spectra. That is correct. Okay, the other major piece of data we're going to be collecting in the experiment are chemical tests. So I would recommend that you read chapter 9 front to back, as it provides a summary of qualitative analysis that we use to assign the identity of different compounds. So for today's experiment, we're going to be looking at first solubility. You should look at the solubility flowchart. And to confirm the presence of unique functional groups, we're going to be doing the Belston test, the silver nitrate test. These two tests confirm the presence of an alkyl halide. The Belston test is more general for aryl, vinyl, and alkyl halides, while the silver nitrate test is unique for alkyl halides and will not give a signal for aryl and vinyl halides. So the Belston test, essentially when you burn your sample on a copper wire, you'll see the emission of copper. And as a result, upon burning your sample, if the halogen is present, you'll see a characteristic green flame. That's a positive confirmation for the presence of a halogen in your sample, such as the bromine atoms that we installed during bromination. Does this Belston test make sense?
Isn't the Belston test the one that is going to search for the alkyl halides in the compound?
Yes, it provides positive confirmation of an alkyl halide.
And then the silver nitrate is the one for the halogen, right? Halide.
Both will serve as a positive test for the alkyl halide. I'm just making the distinction that the Belston test can detect aryl halides and vinyl halides, while the silver nitrate test is specific towards alkyl halides that are reactive via nucleophilic substitution reactions. Does that make sense?
Yes, so Belston is the aryl halides and the silver nitrate is the alkyl halides.
The Belston test will detect any halide. The silver
Okay.
nitrate test is only alkyl halides or halides that are reactive via nucleophilic substitution.
Okay, that makes sense now. Thank you.
Perfect. So the silver nitrate test serves as confirmation that we have these alkyl bromides installed. The silver nitrate test is specific to alkyl halides and will not work for sp2 halides. The reason why is when we treat an alkyl halide with silver nitrate, the silver activates our halide as a leaving group and facilitates displacement of our halide via either an SN1 or SN2 mechanism. In some cases, if you have a secondary alkyl halide, it requires heating to further promote this reaction. Now, you may say, why don't we just detect for this alcohol? Well, the silver nitrate and nitric acid will usually cause further side reactions. However, when the silver nitrate reacts with our alkyl halide, we generate a silver halide, in this case, silver bromide. This is a clearly identifiable white solid, and this precipitate is a clear sign that an alkyl halide is present in our organic compound. So we're going to take our organic compound, dissolve it in nitric acid, and add silver nitrate. If our precipitate persists when we add silver nitrate, that is a sign that we have our silver halide precipitate and we have a halogen present. Does that idea make sense to everyone? Okay, perfect. The last test we're going to do is the ignition test. And if you have an aromatic ring, you would see a dark and sooty flame. If you burn your compound and you see a characteristic dark sooty flame, that's a sign you have an aryl group present in your molecule. So, any questions? So that's a complete overview of the laboratory, what data we're collecting, and how I expect you to analyze the data. Oh, like the flame will be super dark. Like it'll look like there's like dark particles in the flame. And if you pull up the recording when we get to the flame test section, you'll notice the flame color change when you're burning an aromatic compound. It's like the flame gets really dark. And you start to see the really dark smoke emanating from it. Any other questions on this lab? I provided this pre-lab lecture because the lab report is going to be due in 1 week, and this prepares you to watch the video and collect data from the video. So, with that established,